Okay. Okay. So there's what do you call Al Gore playing the drums? Uh, yeah. Algorithm. Okay. Sorry. Okay. Okay. So NP completeness is SAT. Okay. So we did a lot of work, and you did a lot of work on your homework, where you were reducing SAT to everything. You were just saying, oh, I can go from SAT to three-dimensional matching, blah blah blah. So we're going to talk about that. We started to do that last time, and then we're going to talk about how some ways to deal with NP complete problems, right? Because you can't. One thing you can do is when your boss comes to you and he says, you know, you need to solve this problem or something, and then you say, well, it's NP complete. You know, they're not going to, you know, you have to deal with, that's really not going to get you promoted. So you have to deal with these problems anyway, okay? So you could say it's NP complete, but I'm really smart and I'm going to do something anyway. So, okay? So we'll talk about that. Okay, so last time, where are we? Okay, so we're going to show Rudrata path. I went over this rather quickly last time, so I want to just go over it a little bit more because it's kind of a very cute example. And of where it's sort of a subtle thing. The TSP problem has two things, right? One with the triangle inequality. There's these two problems I introduced here. So one where, even when you think about it, if it's a road map, it's a city, the set of cities where you can, you know, going from city A to B, you could also go from city A to C and then C to B. That seems reasonable. That's one assumption. And that's called the assumption with the triangle inequality. It says any two sides of a triangle is longer than the third side if you sum them up, right? You could always go through the other two sides, the other point. So that's a triangle inequality. If you don't have that, if, for example, if you had something that does not obey the triangle inequality, it's going to be a triangle, but it's going to have a kind of a weird condition. This can be 100, this can be 2, and this can be 3. You see, this is not something you might think of a priori when you say you don't have the triangle inequality, right? To go from A to B costs you 100, but from going to A to C and then C to, well, let's call it. Okay, so this is not having the triangle inequality. Okay? So it's kind of a weird example. They do come up, these non-triangle inequality versions, but, and the example I said before is if you go to C, it has a little bit more to do with ordering, but it says you should never visit a vertex more than once. It has that sort of flavor because you're selling stuff that will get you hung, right? Like a snake oil salesman. Has anybody seen these old westerns where these guys would? Okay, so you go to a town, you sell them a bunch of stuff that's hurting them, and then you leave quickly. Okay, and you don't come back. Okay, but now you have to go over the mountain pass to get to the third city. Okay, that sort of thing. Does that make sense? Okay, so so those are the different things, and they're interesting also technically because first of all, this is this reduction we did last time. We said a Rudrata cycle in this reduction. If I set up the distances between any pairs as 1 if there's an edge in here, and I forgot the not again, and 1 plus alpha if there's not an edge in here. The Rudrata cycle implies there's a TSP of cost n, right? Because a Rudrata cycle visits every node once. Okay, and TSP of cost less than or equal to n it means there's a Rudrata cycle. Okay, means you never use an edge, a non-edge in this graph to visit every node. Okay. So the non-optimal cycle is of cost. You have to use at least one non-edge. Yeah. Yeah, it should say not edge. Yeah, so that one should be not. So, okay, so let's see. Oh, okay. Okay, try again. Okay, sorry. Okay, I can't reach it, otherwise I'd cross it out. Okay, so technology. Okay, so if alpha equals 1, this or less, it obeys the triangle inequality. Okay, so that says that the triangle inequality holds, right? Every edge, there's a 1 here, and there may be a 1 here. If this is not an edge, it's at most 2. So the triangle inequality is obeyed in that case. Okay? But it says even with this condition, which could make the problem easier, it's NP hard. So this reduction says even in this sort of simple case, which is very natural, it's not a weird case. It's exactly what you expect. It's NP hard. Okay? On the other hand, if alpha is large, either the cycle is of length n or n plus alpha for an arbitrary alpha. So it says, if it's of length n, you have a Rudrata cycle. Otherwise, there's nothing in between. There's no numbers in between which could be the length of a cycle. So therefore, even if you could approximate this value within some factor, you would actually, the only way you could approximate it, say if you put 100n here, to a factor of 2, is actually to get the right solution. Okay? Because there's no solutions in between. So either you get this solution or you're really off. Okay? So this is it's quite an interesting example because it says you can't, and we're going to get into approximation algorithms shortly, so I just wanted to go over it a little bit more slowly. Okay, you says you can't approximate this particular problem to any factor, and this reduction also says even this thing that seems kind of, natural is NP hard. Okay, it's a simple reduction, but okay. Okay, so now any search problem is reducible to SAT, and what we're arguing is that SAT is NP complete. That's what we're going to show next. Okay. So our 3DM, Rudrata, TSP, all these are NP complete. Why are they NP complete? Well, all problems are reducible to SAT. SAT is reducible to this, to each one of these, right? And so therefore, all problems are reducible to each one of these. All problems are reducible to subset sum. All problems are reducible to TSP. All search problems, okay? And what we mean by a search problem is there's a polynomial time checking procedure, verifier. Okay? So this says all of these are going to be hard. So you don't really, that's what we said intuitively, but really, so the way this springs, and I started this last time, I just want to do a little bit more slowly. This is really one of fundamental ideas in computer science is, basically everything's a circuit or everything's a computer, and which is a circuit. So circuit SAT is a particular problem, which is it should strike you as very generic. Okay, so this is the problem, right? So you're given a circuit, and you want to say if there's some setting of the inputs, which you can make the output be true. Okay? So this is actually a very natural question besides, right? Because this is, if you want to test your circuit, you want to see if it has certain behavior. You want to see if anything is going to make it crash, right? This may be something that you want to do. If anything makes it, that a certain condition may be false, then it should never be false. Okay. For example, this could be a checker that checks whether certain inputs, you can check whether the thing is sorted. So this output could be the one that checks whether something's sorted, and you want to tell if it ever is false. Okay? So what setting of inputs will make this circuit evaluate to the true? So that's the question. Okay, so you're given a circuit, and you're asking what set of inputs, is there a set of inputs that will make it evaluate to true? Okay, so now the circuit SAT looks a little more general than SAT. So once again, we're going to do one of these reductions where we simulate each gate with a set of clauses. And those clauses tell you this gate is operating properly, this gate is operating properly, this gate is if all the gates, and then it's going to have a clause in there with the variable for the output. Okay, so the gate G is a true gate, so you add the clause x sub G, right? When is this clause true? Only if If and only if x sub g is what? What does x sub g have to be for this clause to be true? True. Right? This clause won't be true if x sub g is not true. Okay? Okay, if g is false, add a clause for not x sub g. And that clause is only true if the value x sub g is false. Okay, that's the only way you can make this clause true, satisfied, right? You need to satisfy all the clauses. I'm writing down a list of clauses. Every one of them needs to be satisfied. So for any gate that's a true gate, then I can write down a clause that just says x sub g for that gate, g. Okay, now for an OR gate. So you have x sub g or not h. Okay, so that says that one has to be true, or okay, so let's see why these are true. Okay, so let's look at all three of them. So if h prime and h are both true, then x sub g should be true, right? So that's what that says, right? Because the x sub g or not h, the not h will be false, so x sub g must be true. Maybe this is an and. Is this an and? Oh yeah, that's right. If either one of them is if either one h or h bar, h or h prime are false, are true, then one of these clauses, h bar will be false, and therefore xg must be true. Okay, so these things force xg to be true when either one of these is true. Okay, one other condition you have to say is at least one of them should be true, right? Okay, and that's what this last thing is telling you, that at least one of them should be true. If, what does this say? This saying if they're both false, if these are both false, then x sub g better be false, so not x sub g is true. Okay? So that's the conditions of an OR gate. Is that clear? Yeah. It's just, I just wrote, because h is the name of the gate, and x sub h is the name of the variable. I don't know, it doesn't matter. I could have used h as the name of the variable. I'm translating a circuit into I just want to keep it straight. Yeah, I just want to keep it straight as it's a type polymorphic. You could have done it either way. In the book it does it the other way, but I find it clearer to just separate those things. Okay, so for an AND gate, you can go through what these clauses and make sure that the truth table for the AND gate is also satisfied, right? And then for NOT gate, then these two clauses need to be true. So finally, x0 is true if and only if the circuit evaluates true. So then you have a clause for the output, which is just x0. Okay? Okay, so once you write down all these clauses, you're saying everything is working the way it's supposed to. Any satisfying assignment means there's a way to set up the inputs so that so there is a satisfying assignment. Okay, do people understand? People seem a little, yeah.
So just to summarize, you're translating the language of circuitry into something satisfying with the
Right. He says to summarize, I'm translating the language of circuits to just sets of clauses, which is what SAT is, yeah. Yeah, I believe you do. Okay, so but why do you need it? So you have 4 cases, right? So if but one of them symmetric, so 3 cases really. One of them's true, both are true, and both are false. So if both are false, it better be true that this is false. Okay, that's what this clause is ensuring. Okay, that's why you need that one. Okay, and now the first clause is ensuring that if h is true, that the output x sub g will be true. Okay, so for each one of those clauses, it's one of those 3 cases in this case. Okay, okay. So Okay, so that says circuit set. This complicated circuit can be, I mean, it's not so surprising, right? You say, okay, well, this gate better be working, and I can write that down in a set of, and this better happen, and this better happen, and this better happen, this better happen. You could write out a truth table. That's what we're doing. Okay, for each gate. Okay, so now I want to say all problems, every problem, no matter what problem you give me, as long as it's a search problem, I can reduce it to set. And this is, again, one of these really sort of striking but trivial things, right? Striking because it's like any problem. It doesn't matter, right? Hey. Okay. So reducible means polynomial time. It's just because our definition of reducible. Yeah. Yeah. He asked, well, what's so special about a polynomial time computation? Nothing. Okay, actually, it's just our definition of what reducible is. So the polynomial, what the real statement should say, is all NP problems are polynomial time reducible to circuit set. Okay, and the statement for NP is search problems where there's a polynomial time checker. Okay, so that polynomial needs to be in both places. So if you said, I have a solution that could be solved in logarithmic time on a parallel computer, I should have a logarithmic reduction. Okay? So you can do this. There's other classes. This sort of infrastructure for translating one problem to the other, just generally you need to say the way you translate it should be no more costly than the cost of solving it or checking it. Okay? So there's that sort of self-similarity. Okay, so lots of reductions. So how can we do this? The problem is there's a lot of problems, so you have to do lots of reductions, right? That's always a joke, right? But you guys are all sleeping or something. Okay, oh my God, there's so many reductions. How many reductions are there? Well, when they sit around the house, they sit around the house. Okay, so you've obviously not heard that joke. So when they sit around the house, they sit around the house. Okay, so it's actually about somebody's being overweight and not politically correct, but okay. So, all right. So, okay. So a search problem. What it means is there's a program which checks if S is a solution in polynomial time. So you're right. These should all say in polynomial time. We have a certain religion that we mean polynomial time when we say a solution, but I should put it. It's important. Okay. So example is a Tor. Is the Tor a solution T? If I give you a Tor and a TSP problem, can you check it in polynomial time? Yeah. What? Oh yeah, I need a budget too. Is a Tor a solution to a TSP problem? So the TSP problem has a Dij and a budget, right? That's the search problem. It checks the length to see if it's inside your budget and if it is a valid solution. So what's an example for SAT? Can you write a program? Is it easy for you to see how to write a program to check if the assignment is that? Okay, so that's what I mean. There's this program. So this program here is just a program. It's just a piece of text, right? From that piece of text and a particular input, I can sort of generate a circuit. Okay? I could say, what would the computer do on line 1 on this input? What would it do on line 2 on this input? Okay? But I don't actually know the input, right? Because the input is what part of the input do I know and what part of the input don't I know? Right? It's a P of Si. I know I. I know the instance. But I don't know S. Right? Those are the unknown inputs to my circuits. Okay? So there's a part of it that I know, which is I, and a part of it which I don't know, which is S. Okay? Okay, so then with the circuit, I can, so I can translate this into a program, anything that's a program and some size input. If I guarantee you it's not going to run longer than something, I could always just write out the circuit for that many steps. I could unfold the computer for that many steps, and therefore I have a circuit. Okay. Okay, so this is something you learned in 61C. Did you learn this? Who learned it in 61C? Sort of. Yeah. Okay. So, okay. For instance I. So for each instance I. Now this thing does know the inputs for I. It doesn't know S. The S is going to be an input to the thing. So you can generate a circuit. Remember, when you want to translate one NP complete and one problem to another, what you want to do, what that means is you take an instance, a particular graph in vertex cover, and translate it to dominating set, to a different graph possibly. Okay? You take a graph here and you take another input here. So for a particular input of your problem for which you have the program, and you have an input and a program, you can generate a circuit. Okay? And then you hand that circuit to the circuit solver in some sense. That's intuitively what you're doing. Okay? So if and only if the circuit is satisfiable, there's a solution to the original instance, to this original instance of the problem. Okay? Yeah. Right, because my computer is only finite size, yeah, and so therefore we can just say the whole circuit in your computer. Your computer is a circuit, right? One step of your computer is just a big circuit. It's constant size. Okay, so that's why you know. Okay, so technically there's one thing about your computer that's infinite, and what is it? Yeah, our view of a computer, there's one thing. So yeah. Yeah. Do you get that? Memory in your computer is infinite. That's our model of a computer in theory. But here, you know the memory is polynomial in size because you know the running time of the program is only polynomial in size. So then you just allocate that much memory and you say, well, I can't run out. Okay? Yeah. You could have a bad circuit for it, but in some sense, if it's a polynomial time, it's not. So we got to be careful what the terminology is. He asks, is there a polynomial time problem with an exponential size circuit? So what we mean by a polynomial time here is not the problem. The problem here is we don't know a polynomial time solution for the problem. What we know is a polynomial time program. We know we have it for this problem with a solution, to check the solution for the problem. Okay, we have a polynomial time problem. We're given that. Okay, so that's what we're assuming up front. In the very first page in the chapter, we said, what is a search problem? A search problem is a problem where if you're given an instance and a solution, we can check it in polynomial time. Okay, so that's what we're saying. Okay, so an NP problem is not by itself a polynomial problem because it's not in polynomial time because we can't find the solution. This doesn't say anything about how to find the solution. It just says we can check it. Okay. Mm-hmm. There could be circuits of size. There could be exponential size circuits for an input instance problem. There are definitely problems where you need exponential size circuits. Yeah, that's right. So for those problems, but we're not talking about problems with the exponential size checking circuits. We're talking about problems that we're given, in some sense, a polynomial time circuit for. There are definitely problems you can't solve that aren't even in NP, right? For example, if you took 70, you saw the halting problem. That's not an NP. That you can't solve in any amount of time. Okay? So this is only a class of the fact that there are problems that are not an NP are there, and those could be exponential. They could be never. There are things that are harder, but NP is the problems that actually come up a lot. Okay, these search problems, right? You want to find the best solution to blah. You want to find the best solution to this. You want to find that's something that's natural. Okay. So this we have a reduction to circuit set. Okay. Okay. So now we're basically we're screwed, right? All these problems are hard. Every one of those problems I put on that list, and everything you're going to ever have to do in your life probably is NP hard if it's optimization. Okay, so we already told you the easy ones. They're in the book, and there's a few hundred more, and every other problem, which is a few gazillion more, is NP hard, right? So it's really really common. Okay, so what do you do when you're faced with one of these? Okay, sometimes there's easy versions of the problems, and we saw some of them, like 2-sat versus 3-sat. 2-sat was easy. We gave a solution for 2-sat. It was in the homework. The Horn clauses, they were easy. So sometimes these come up. You know, sometimes you can do NP. You can solve NP complete problems on trees. Okay, so and that's a graph, but it turns out to be easy. So if you look at your problem and say it's NP hard, but then you're working with the tree, that's okay. You can still solve it. Okay, so for all these graph problems, the ones that we showed were NP hard in general aren't NP hard on trees. So that you sort of run out of examples there. Like for even planar graphs are hard. Even 3-sat is hard, right? Satisfiability with just 3. You think 2 is easy, and then 3 is hard, right? Matching is easy, but 3-dimensional matching becomes hard. Okay, so it sort of runs out. So what to do? Intelligent exponential search. As an algorithms person, I must choke on it. Intelligent and exponential, right? It makes me gag, but okay, that's what people do. Okay, I should have actually included a little bit more here, but so we're going to talk about backtracking and branch and bound. Okay, so you've seen these before, but we'll go over them again. And this is efficient enough in some cases in practice. For example, right now, and this is something you should pay attention to, what I'm saying next, so you might find it useful. There are SAT solvers out there which are really quite good, and they're highly tuned and highly optimized. Okay, so and they do some version of this search and heuristics and. Okay, so we're also going to talk about things that provably get close to optimal. So maybe you don't find the best solution, but I can give you an algorithm that is polynomial time, and it has a bound that gets within some factor of optimal. Have we seen such an algorithm? Right, that's the set cover. The greedy algorithm for set cover provably gets you within a log factor of optimal. Okay? Okay, so sometimes that's good and sometimes that's useful. Heuristics, okay? So, you know, heuristics are you're not even guaranteed, nothing is guaranteed. The search and the bound. At least exponential search in branch and bound and backtracking, you will get the right solution if you're willing to wait long enough. Okay? So heuristics are, okay, let me try this and let me fix it up a little bit and see how well I do. So the heuristics may not converge in polynomial time, and they may not give you the right answer. Okay, so but still they're very useful. So we'll over the next couple of lectures we'll talk about those. Today we'll just talk about backtracking and branch and bound. I might let you go early, but I'm going to show you a demo. We'll see if it works. You'll want to see it though. Okay, so backtracking. So what is backtracking? All right, so. Let me give you an early break, because I think I might let you go early. So, and I'll get into backtracking. Okay, so. Yeah.
Is what we're going to talk about, is that to do with pruning as well, or no?
Yeah.
That is basically pruning?
Branch and bound.
Well, that's what...
Bound. That's what bound.
So can pruning, no matter how much you prune, that's not going to increase, like, help the runtime? Right?
It will help it, but it won't make it polynomial.
It won't make it polynomial.
It'll help it a lot.
That's much better.
Yeah. Yeah, there's one exponential and lots, right. Yeah.
I heard that 172, 174.
What?
I heard that 172 and 174, CS 172 and 174 were going to be redances. Is this true?
Yeah, I don't know. Yeah, I don't know. Who'd you hear that from?
Friend mentioned
Who's his faculty advisor?
I don't.
Okay. Yeah, I don't know. It's possible. Right now we have we got this huge grant. I mean, not a huge grant, but so the theory professors are many are involved in that. I'm not, so I'll still be teaching, but I have to cover the courses. Yeah. So at this point, it's not clear how we're going to offer them. So there's an issue with that. So, but we're going to try. But we may have a little gap next year. I'm not sure we'll offer it. But yeah. Yeah.
The contest at the end of the semester, so it is a mandatory homework assignment.
It's not mandatory. Yeah. Okay.
I had a quick question.
Mhm.
So is factoring NP because in the book it was like you can't really consider factoring NP because there's always a solution to factoring, and in NP there's a case where there might not be a solution. So would it be considered NP or?
It's NP. The question is whether it's NP complete.
Okay.
It's in NP.
It's in NP.
Yeah.
Okay.
Because it's either prime or you don't know. There is a yes and no answer.
Well,
It could be prime.
but it's still you can still factor it. Could be no.
Yeah, but it's just a technical. It's just how you define it.
Okay.
The real
It's
question.
It's what you define as like no answer.
There should be a no answer in general for it. But that's just a technical thing. I mean, morally, factoring is you're asking whether it's prime or whether there's factors. So that version of factoring, if you pose it that way, it's certainly an NP, a search problem.
But is it really checkable in polynomial? Because what if the numbers were like huge? Like,
Yeah.
and even if you're multiplying together, like.
Yeah, you can. Sure, you can. N squared.
Yeah.
It's N squared.
Okay.
It's N squared, which is fine, right? Okay. 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 All right. So okay. All right. So you get an answering machine. So I called up this answering machine and said, the number you have dialed is imaginary. Please rotate by 90 degrees and try again. All right. Sorry. Okay. So all right. Okay. So let's see. What is it? Yes. Okay. Okay, so now backtracking. So is this formula satisfiable or isn't it? Who thinks it's satisfiable? Okay. Who read the lecture notes before lecture? Okay, let me give you another lecture. Okay. So this is like a lecture I give to my kids, right? So you should read the book before you come. And then you can complain on HK and, he just does what's in the book. But I guarantee you don't understand the book. Okay, well, there's one of you out there who does, okay? But maybe three. But just reading the book you're not going to get it. So go read the book, come to lecture, you get much more out of it, right? So look at it ahead of time. So for all your classes, for everything, you'll do way better. I mean, you're going to do it afterwards anyway. And so it's a really big deal to do that, to prime your mind. Professor Sinclair, he says, you need about 10 times through something before you get it. Okay? So lecture is worth a couple, but it's worth more if you've already done at least a pass through the notes. Okay? So this is actually formula right out of the book. Okay? So we should know whether it's satisfiable, maybe. Okay. Okay. Is that the right one? Okay. So this is the formula. So what we're going to do is branch and bound. We're going to start with the original formula, and then we're going to set one of the variables to be true. Okay? We're essentially going to try every possible assignment in a sort of just in a methodical way. So one thing we can do is we could set this variable w to be true. So now if we set w to be true, the blue clause is there. What happens with the blue clauses? They're satisfied. Do we need to deal with them anymore? No. What happens with the red clauses? They're not necessarily unsatisfied, but yeah. Yeah, so what happens is z or not w if w is false. I mean, w is true. So not w is false. So what has to be the case? Z has to be true. So you get a new clause. In this condition, when you set w to be true, okay, so pay attention, right? This is like this is what you're going to be doing a lot of, okay, shortly. So z or not w, right? When you say w is not true, what you need to now figure out is how does this change the problem? Now I'm getting a different problem, okay? So the problem, what I'm going to get is a new formula where all the blue clauses are gone because they're satisfied, and the red clauses are reduced, right? You lose an opportunity to satisfy them with this assignment. Okay, so you get this new formula, right? X or Y, that's the blue. That's the blue. That's the blue. The Z comes from this one, and the Z bar comes from this one. The X or Z should be in the middle. Okay. Okay, so now for w equals false, now we have them switched, right? The old ones that were blue are now red, right? Because those are a little dangerous. So those are the ones where this guy doesn't help us, right? The blue ones are good. We're all good with the blue ones. Okay? So actually, is this formula satisfiable? Now can you tell? Because it has a z and a not z. So we're done with this, right? With that side. We don't have to explore it anymore. Okay, so now we have w equals false, and we replace the things. The red lose their w variable. The blue go away. So we have this new clause. Okay. Now, if we set x to true, the blue ones are these here, and the red one is the not x, right? And that's a problem, right? What happens there? You get an empty clause, right? So there's no way to satisfy an empty clause. That's just a convention that the book uses. So this says there's no way to satisfy it, given that w equals false and x is true. Okay? Is that clear? Okay, so now x is false. So there, the red ones are these guys. This x doesn't help these values. The blue one, it satisfies that clause. That clause gets deleted from your new problem. So you get this new problem. Okay? And you could set z, and then once you set z, you get these. So now do you know whether this formula is satisfiable? It's not satisfiable. Okay, so this is the hard case, right? Like with the satisfying assignment, I could have just told you the assignment, you could plug it in, it would have been really easy. Okay? This one's not satisfiable, so in some sense we have to prove it. We have to prove every which way you move, you can't find a satisfying assignment. So technically you could have to search over everything with this search. In this case, it turned out to be not so bad, okay? But this no instance, this thing where you say, oh yeah, this isn't satisfiable, it really requires search, right? I mean, you can't get lucky here. You have to prove, no matter what, that there's no satisfying assignment, and that's what we've done in this backtracking search. Okay. Okay, so there are a few choices here. So which subproblem does expand? In some sense, if the answer is going to be no, maybe it's not such a big deal, right? Maybe there you could also, it is a big deal even if the answer is no, but it's harder to see. But if the answer is yes, you want to shoot for a satisfying assignment, or maybe shoot for a contradiction. Either way, you want to sort of see what happens. So perhaps the subproblem with the smallest clause and variable in that clause, because the smallest clause is the hardest one to satisfy. Okay? So in this case, right, once you get an empty clause, you know you need to go no further. So why explore variables that are in lots of clauses? You would rather check whether this clause is going to get you messed up going down this path. Okay? Okay, so for each, like in this one, instead of exploring x, I could have explored y. Right? But by exploring x, I sort of learned something right away. I could have explored y and then had to explore x later. So the tree shape would be different depending on the order I did it, even for the no instance. Okay, so this way of generating the counterexample was better because I more quickly found this termination point. Okay. Okay, so that's which variable to expand. So these are some heuristics that they use. For each problem, what do you need to do? So generically, if it's not just a assignment problem, say you have a generic problem that you're given, what do you need to do? For each subproblem, you need a quick test for fail. What was our test for fail in the assignment problem? He said see x and not x, for example, or seeing an empty clause. The book has it going one more, and you see an empty clause. Okay. So you want to check if you succeed. Okay, that says, well, all this. When do you succeed in this case? What does your formula become if you've succeeded? Empty. No clauses. Okay. If you have no clauses to satisfy, everybody's satisfied. Right. That's why it's really good to have a boss, because then to not have a boss, because then they're always satisfied. Okay. So fail and succeed, and then maybe. You have to go on. So maybe is not enough of an answer. When you have a maybe, you also have to expand into subproblems. So this is generically what you do in backtracking. Okay? So if it's maybe, I don't know whether it fails or succeeds, then you need to go further. And in this case, that was pick a variable, and then set it to true and set it to false, and now I have two subproblems. Okay, so that was the way it was done for SAT. Okay. Okay, so now backtracking. Okay, so you can do this in backtrack. Now you can do this generically. So you start with some problem. Okay, which is in our case was a formula. We have the set of active subproblems. So we repeat while the set is not empty. We choose a subproblem from the set. We remove it from S. Okay, expand it into smaller subproblems. In this case, we chose one of our formulas that we were working on, and then we expanded it into smaller subproblems. Which the way we did that is we picked a variable in that formula and set it to true and set it to false. And now we have two other subproblems. And then we add them to S. And we keep processing S. Now for each subproblem, you first check if it succeeds, if you found a solution, for example, the empty formula. Then you halt and say you found a solution. If it fails, you discard that problem. Okay, so if you have an empty clause, you say, I'm not going to explore this particular problem anymore. Otherwise, you add it to S. Okay? So, and if at the end, in the middle, you would have broke out and said there's a solution, right? If you go through this loop and have nothing else to do, if all your problems failed, you announce there's no solution. Okay? Okay. Okay, so that's fine. So now this is what you do to get, for like something like satisfiability, where you just want to get a solution. But in the world, what you often want to do is get the best solution. Okay, so for SAT, it doesn't make so much sense because all you're trying to do is find some assignment that satisfies your clauses, but the shortest traveling salesman problem. So this is the shortest. Okay, again, we're flipping a little bit away from the search problem and going morally to what the search problem is trying to do. Whenever a search problem has a number associated with it, really what you want to do is just find the best value for that number, right? It's an optimization problem, really. So the shortest, what you want to do there is you want to find the shortest traveling salesman tour. You don't want to find for some number B whether there's one of B. The way you do that is you find the shortest one and see if it's less than B. Okay, so the real problem in those things are when you're given a quality measure is that you're trying to find the shortest. Okay, so now for optimization problems, what should we do? Branch and bound. So it's just like backtracking. So you start with a set, some partial solution. For a TSP tour, what's a partial solution? Yeah, he says it's a subset of cities you visited so far. Okay? So in particular, what would you start with? What would the first one be? Yeah, it could be a starting vertex, or it could be the empty vertex, but I would make it a starting vertex. It's nicer to make it a starting vertex because you need to still do these things. Here, let's see what so then you figure out what the best so far is. It's infinite, right? You're trying to find, this is a minimization problem. We're saying we're trying to find the smallest tour or smallest vertex cover. Repeat while S is non-empty. You choose a subproblem. You remove it from your set of problems that you're thinking about exploring, and you extend P into a bunch of subproblems. So for TSP, a subproblem is my path so far, right? So now if I pull a path so far out, and that's a partial solution to my problem, right? So now how would I extend it? What problems would I get? What would my next problems be? What would be the set of problems? Anybody? So one set of problems is, well, I try every possible extension of this path, okay, and say then I get a path of one that's one longer for every possible way to extend this path. Does that make sense? Okay, so for each PI, if it's a complete solution, then I check. If I have a tour now, then I check if I'm done. I check the cost of that tour, and I update best so far. If the cost of that tour is better than any tour I found before, I update it. Otherwise, I do something a little bit funny here. I say, is there a lower bound of P? If that lower bound is bigger than best so far, if it's less than best so far, then I add PI to S. So I'm going to do something a little bit clever in branch and bound. This is the bound part. For a TSP tour, the MST is a lower bound. The cost of the MST is a lower bound. Okay, why is the cost of the MST a lower bound? Because a TSP tour connects all the nodes, okay, just like an MST does. But an MST is a way to connect all the nodes with the minimum cost. So the MST cost is less than the cost of the tour. Okay? So for the TSP problem, I compute a lower bound based on this path. I take the path so far, I'd rip it out, okay? And then I say, well, what's an MST on the rest of the graph? And then add the length of this path. And that's the lower bound on my solution. Okay? Okay, so then I return the best so far. Okay, so if the lower bound is less than the best so far, then I add PI to S. Otherwise, if it's greater than it, I know this partial solution will never lead to a better solution. Okay? Okay, so can we perhaps do a bit better? Okay, so this is branch and bound. Yeah. Okay, so that's not what I'm looking for, yeah. So is there a way to sort of just minorly modify this program? So the bound part is I'm not going to explore partial solutions which I know suck, okay? That's the bound part. So where's another place in this procedure that I can do better? Where do I have freedom in my solution? When you have the freedom to choose. Okay. So where do I choose here? Where I say choose. So which subproblems should I choose? Yeah. Yeah, but that my lower bound is the lowest. Okay? Because the lower bound says my solution is at least this bad. So I might as well pick the lower bound, the one with the highest lower bound. Okay? Okay, so now is that has people people heard of that? What is that called? What procedure is that called? Anybody? Has anybody heard of A star? Okay, so those with the lowest lower bound. Okay, so I don't, there's, computer scientists, I don't know whether you noticed, but we can be kind of geeky. So sometimes when you call something A star, people have very particular phrasings of what A star means. Oh no, that's not A star. But more, that's why I put ish. So I think it is A star, but if not, it's morally the same thing. Okay, so okay, so then when you start with, you do the natural thing, except you extract the partial solution with the lowest lower bound. Okay, so it's the same algorithm, except you do this, and then you return best so far. Okay, so do people see this algorithm? Okay, so A star is phrased with goal states and starting states and path to get there and path from there. I'm sort of burying that all in the lower bound, and you'll see how I do that in a moment. Okay, so the demo. Okay, let's do a demo. All right. Okay, keep your fingers crossed, one way or the other, depending on whether you want to see somebody fail or you don't. Okay, so first of all, let's look at. Okay, so here's a graph. Is this a graph? Do you see a graph there? Okay, so there's a graph. Okay, so let's see if we draw the graph here. Okay, so we have nodes. Can you guys tell me what's on the graph? You just want to see if you can read it. So is there an edge from 1 to 2? Okay. Okay, 0.125? Okay, is there an edge from 2 to 3? Okay, 1 to 3. Okay, so okay, and is there an edge from 1 to 4? I just want to get you guys to parse the format. Okay, 2 to 4. Okay, we want to compute the tour for this. Okay, what's the tour? What's the optimal tour here? Anybody see it? Uh-oh. $2.45. Oh my God! Somebody saw it. Okay, so at least that's what the program says. I hope it's right. Okay, so what's the tour you had from 1 to what? 1 to 2. What's the next one? 2 to 4. Okay. This seems bad because we're using the biggest edge, but what do you know about this? Do you have to use this edge? Yeah, it has to have 2 nodes, 2 edges next to it. And then what is it? 4 to 3 and 3 to 5, right? This is the TSP. That's the TSP tour for this one, right? 1, 2, 4, 3, 1. Right? Okay. Okay, so that's the tour. So let's see how we're gonna solve it. Okay. Okay, so we're going to do What does it say we're going to solve? How are we going to solve it? A star. Okay. So we're going to solve it with A star. Let's look and see what A star does. Okay. So it does more or less what our thing says. The best so far is there. Then we have the set S, which we're adding partial solutions to. This is the best so far, and the solution should actually be together. Who wrote this code? Okay. I wrote this code, but okay. So these two together are telling us what's the best we've seen so far, and the solution. Okay, A star, what does it take? It's generic, right? It takes a lower bounding procedure. It takes a when I'm done procedure, an expand procedure, and what's a big value? What's infinity? Okay, so it's all generic. It's exactly the code. It's essentially, let's see, is it in here? Oh yeah, it's this. See, this is the LaTeX of branch and bound. Okay, so I just implemented this. Okay, generically. Okay, so search. Okay, so you take these various procedures. This is the beginning problem, and these are the procedures that you need in A star. You need to explore, expand, see when you're done, and evaluate lower bounds. Okay, so an A star does all those. It picks a problem to work on. This task queue either is a priority queue or it isn't. Okay, so we're passing into the task queue the lower bound, the bound, when we're adding it to the queue. Okay, so then this is a counter to see how many nodes I explore during the procedure. I think this should be okay. So so then what do? You pull a task out if you're done. If this is a full solution to your, say, TSP problem, you check if the bound you have for this problem, this lower bound procedure also checks full solutions. For there, the lower bound should equal the value of the solution. If it's better than the best so far, then you store it. You store that solution. Otherwise, you expand. This is a generic procedure that expands to the next step. Of course, people who really know Python probably realize I really don't, but that's okay. It works. So I'm probably not doing any of this the Python way, but I think it's maybe more clear. So these are just print statements. Okay, so then for each of the new problems, I insert them into the queue. Okay, does that make sense? As long as they're lower bound. Okay, so this is stupid if commented, and you'll see why. Okay, so there's this commented line that says I only inserted it in the queue if the lower bound is lower than the best so far. If the lower bound is higher than the best so far, I shouldn't put it in the queue. So we're going to see the effect of doing this solution poorly. Okay, so that's it. So now we're going to solve a TSP problem. So now you want to say for each one of these little subroutines, what did we do? Okay, so for the TSP, it's really probably slow and inefficient, but what I do for the TSP lower bound is first I remove the path here, the path that's in there, and then I remove the edge, and then I compute the MST cost of this new graph of everything else. So I have a path. So I have some graph, and it's weighted. And right now I'm working on some partial solution, which consists of a path. Okay? So then I take this path out, and it has a cost associated with it, 0.4, 0.4. And then now I have a new graph without this path. Okay? And now I compute the MST on that, because I know my graph has to be connected. Okay? So then I say the total cost is at least this, plus the cost of my MST outside. There's a little glitch I need to do with the first and whether you're allowed to use this edge or not. Because once you have all the nodes, you are allowed to use this edge. When you don't have all the nodes, you're not supposed to use this edge. Okay, because you have to connect all of these. So you remove the edges in the path, you remove the nodes in the middle, and then you have to, all these need to be connected. So you need to, the MST is a lower bound on what you can do here. Okay? Okay, so that's what this is doing. It's removing all these things I'm saying. I'm removing the path, I'm removing the edge. I'm removing the path, but for the first one and the last one, right? This path list is not taking the whole path. It's leaving off the first one and it's leaving off the last one. Okay, then you remove the edge between the first one and the last one. Sometimes you need to do that, sometimes you don't. And then there's so then you return the min cost, the minimum way to connect the rest of the graph, plus the cost of the path. Okay, that's your lower bound. Okay? So now, when you want to expand, then what do? For each of your neighbors, here we're using a graph. So each one of your neighbors, you should extend your path to each one of your neighbors. That's what this does. It appends your neighbor to a path, and then it stores it in the, it does some crap to get the formats right, and then it stores it in this result. Okay, and this result is going to be a list of problems. And this list of problems is given back to A star to put back in the queue. Okay? And what else do you need to do? You need to know when you're done. When your path has length equal to the whole graph, then you're done. And that's it. So then you have test code, because you always write test code, right? You always write test code. Otherwise, it would never have worked, right? So it's a lot of test code. Okay? And then that's it. You're done. Right? Now, if you want to do something else, you just need to write your own lower bounding procedure, your own path expanding procedure, your own done procedure. And then you have A star. Okay? So what is this graph? So let's look at another graph. Well, shall we run it? Do you want to see if we get one? What were we supposed to get here? Okay, the output should be the solution 1, 2, 4, 3. That should be the solution for this one, right? Okay. Oh, that's not the right one. Uh-oh. Got my tricks. Okay, so you can see what it's doing as it's going. So it starts out processing path consisting of just one node. Then it generates the new problems, which is there's an edge from 1 to 2, so it adds a problem corresponding to the path from 1 to 2. It adds a problem for corresponding to the path from 1 to 3. It adds a problem for corresponding to the path from 1 to 4. Then it picks one of those problems to process, and then it processes it, and it extends that. There's only one edge from 3 that hasn't already been used. That's to 4. Okay? And so on, right? So each time it pulls out, it says I'm processing this, it generates a list of subproblems, and then it moves on. Okay? So, and in the end, the full solution is 1, 3, 4, 2. It's 1, 3, 4, 2. 1, 3, 4, 2. Uh-oh. Okay. That's good. So it's 1, 3, 4, 2, right? Doesn't matter. Okay? Okay, so now let's look at the next problem we're going to look at. Okay, so I didn't make a figure, but this is the graph. Okay? It's the graph from the book. Okay, so we're going to look at that problem and see how it does. Does that make sense? We're going to explore another aspect of this program. So the value is 2.3. What does it say? Uh-oh. Okay, so I don't know. Okay, so let's see. Problem is, okay, so it does the same thing. It goes through these various things. It goes and blah, blah, blah. Here's a graph. Here's a graph representation. You have these A to B is 2, A to F is 1, right? You see that? and then we're going to run it, okay? I already ran it, but okay. Let's see what happens. Okay, so you can see it going along, building new values, right? So at some point, it finishes a solution here. That's a crappy solution. That's my big number. The 10,000 is I just threw in 10,000. Anything that's 10,000 is crap, right? And so you can say full solution. So there's another full solution which is crappy. It's not connected. There's another one that's not connected. There's another one. There's another one. Okay. So in the end, you get this solution. Okay? You get A, H, G, D, C, B, E, F. Okay? Where and the cost is 8. Okay? So let's see if that's what the book says. So it's A, H, G, D, C, B, E, F. Is that what we got? A, H, G, D, C, B, E, F. Okay? So so now let's look at this other thing. It says the total number of nodes explored was 112. Okay? So let's do a few things here. Okay, so let's do this. So what are the nodes explored? The nodes explored is how many subproblems you looked at. Okay, so let's see total. So the nodes explored, every time you pull something out of the queue, you add 1 to this counter. Okay? So every time you process a subproblem, you add 1 to this counter. Okay, so the nodes explored are the number of internal nodes and leaves in that tree. Okay, so let's see. So let's change this. So what we use is a priority queue. Now what is it? Is it A star anymore? If I change this from the I take in the lower bound every time, and here I don't take in the lower bound. What have I done? What is the keys in my queue are all the same, right? An input is this lower bound, this priority. So I pass in a priority for my path, the length of my path, or this length of this path plus the MST. And what I did is I overrode it and said it's always 0. So now this is no longer A star. This is branch and bound. Or this isn't even bound. Let's see. Let's make it branch and bound. Search. Okay, so this is bound. You only add the task if the lower bound is higher. So this is branch and bound. Okay? So let's see how long it takes. So here we do better, because I did 2 things that made it better. But here, let's do this. Okay, so this one we did better because I made it branch and bound, right? I said, okay, search. So what I did is I commented this in. This was gone, so I was adding task even though the lower bounds were telling me this thing is never going to lead to a good solution. So by doing this bounding, this is this pruning that you do, I've dropped from 112 to 76. So I've done less work by doing that pruning. And this is a small problem. So for big problems, you could do much better. You could save exponential time, right? You could save a lot. You'll run for a lot longer, and you'll save, instead of factors of 2, factors of hundreds or thousands by doing this bounding procedure well. And if you do the better you do the bounding procedure, the better lower bound you have, the more you think about this MST. This is not a trivial thing to figure out this MST, figure out this path. To do that was worth it. I mean, in this case, it's a small problem. It didn't seem like it was worth so much, but it will be, okay? And let me show you. Okay, so now that's where you use the bound. Okay, so now let's do A star instead of branch and bound. So that was 76, and here, search. Okay. So I don't want to overwrite the priority, so now I'm actually going to do A star. Okay, so Okay, any guesses? Who wants to guess on how many nodes I explored? Who thinks it's going to be less than 50? Okay. Who thinks it's going to be less than 20? Okay, so I don't know what it'll be. Let's see what it is. Okay. Who thinks it's going to crash? Okay, let's see if it crashed. Ready? Right? Right? So choosing makes some difference, right? And this is a tiny problem. Going from 176 to 20 is not, it's only a factor of 8, right? But you'll see much more, okay? So now let me go back to the lecture here. Uh-oh, I killed it. Okay, so let me try to go back to the lecture. Okay, events, lecture 24. Okay, it's my birthday. It's not my birthday. It's a. You know this Beatles song? It's today's your birthday. It's my birthday too. Okay, so now it's your turn. Okay, so you're going to do this. Okay. Okay, so we're going to find the best connected dominating set. You're given, in this problem is G equals VE. Find as small as you can subset of S, such that S union, the S and its neighbor should be the whole, all the nodes. Okay, S is a connected subgraph of G. So there's two parts to this problem. Okay, you want to make a program that solves the problem and does as well as it can. You want to generate hard examples. Okay, so you want to generate examples that are hard for everybody. Why do you want to generate problems that are hard? Because how are you going to be graded? Okay, you're going to be graded on how well you do on everybody else's problems and how they do on yours. Okay, so if you make everybody else's programs do poorly, that's your grade goes up. If you do well on everybody else's examples, your grade goes up. Okay? Okay, problem size is 100 applications. There's wireless modes. There's applications there. Okay? So we had announced that the last problem set was required. Okay, so we're making this be the last problem set, so we give you a little bit of a break during part of our week. We will issue a problem set for your study purposes, but we won't give you one that's due. But part of this is due during our week, okay? So look on Piazza, and the homework is posted. But this is not required. If you want to, it's based, oh yeah, there's teams. There's teams of 5, and grab a team, okay? You should do it. Okay, so it's a homework. Okay, everybody listen, it's a homework. Okay, it's part of the homework. This is the 13th homework, okay? So you could drop the 13th homework if you want, okay? But it is one of your 2 homeworks that you drop. Yeah. Any programming language at all, okay? So.